Hello, everybody. Thanks for joining our webinar here. It's 12:55 and we are still coming on here. Thanks for everybody that's joined us so far. We will be starting at the top of the hour, so stay tuned. Hello, everyone, and welcome to today's webinar. Today, we're going to discuss how FT-NIR spectroscopy can enable applications in polymer manufacturing from the lab to process. I'm Brian DeVers, Product Manager for Quantum Analytics, and I'll be your moderator for today's event. A quick note about quantum analytics. Before I introduce our speaker here, we are a value-added distributor of analytical instrumentation in the US and Canada. We offer equipment financing combined with technical services like cross-platform installation, training and product support, and much more. For over 30 years, our company has helped Researchers, scientists, and chemists get the best-in-class instrumentation they need, combined with technical services that help labs maximize their uptime. We offer solutions for a variety of applications, including gas chromatography, liquid chromatography, mass spec, organic and inorganic elemental analysis, TOC analysis, XRD, XRF, and X-ray microscopy, infrared, near-infrared, and Raman spectroscopy. But today, we're going to focus on FT-NIR spectroscopy instruments from Bruker. Today, our webinar speaker is our guest, Robert Feigley. Rob is an independent consultant for spectroscopy applications, specializing in NIR spectroscopy for process automation. Robert has developed numerous applications for both laboratory and process measurements using NIR spectroscopy in the pharmaceutical, food and beverage, polymer, petrochemical, and agriculture industries. He possesses extensive knowledge and experience in chemometric modeling, installation, and training using spectrometers, and has written both application reports and research-based summaries for numerous verticals that use spectroscopy. Robert received his BS in chemical engineering from the Johns Hopkins University. Before I turn it over to Rob, I wanted to review a few housekeeping items as excuse me, a few housekeeping items. As a registered guest, you are going to receive a link to this recorded webinar in your email when it becomes available. This webinar also includes a Q&A section at the last about an hour or so in this presentation. So type in your questions at any time into the question module in the webinar control panel there you see. And Rob and I will be answering questions at the end of the webinar. So this ends our introduction. So without further delay, let's get it started. Robert, take it away. Oh, Rob, we got to get you unmuted here, buddy. Here we go.
I think I'm unmuted now.
There we go.
We got you. Awesome. Hey, everyone. Thanks for tuning in today. And many thanks to Quantum Analytics and Brian for having me today as well. So I know there's a lot of people with, some different backgrounds here. Maybe you're a spectroscopist. Maybe you're an engineer that's in polymer manufacturing. Maybe you know some stuff about NIR, maybe you don't. Maybe you're in another industry altogether, and you've had this, laboratory unit sitting there collecting dust for a long time, and you want to take a closer look and see what these things can do nowadays. So I think there's a little something here for everyone. So let's get to it. So here's a graph of the electromagnetic spectrum. So near-infrared spectroscopy is based on molecular overtones and combination vibrations from about 800 nanometers to 2500 nanometers. You see the NIR on this graph, and I like this one because it shows the wavelength, which is measured in distance, and also the wave number, which is measured in frequency. So near-infrared spectra create a fingerprint of your sample by light either passing through it or reflecting off of it, and then the subsequent radiation interaction, after which the light is collected by a detector, and that light will include data that's related to both the chemical and the physical properties of your sample. So instrumentation consists of a light source, a detector, and a dispersive element that allows the light intensity at different wavelengths to be recorded. The Fourier transform, the FT spectrometers, they work a little bit differently. They use an interferometer to record all the wavelengths simultaneously. There's some definite advantages to that, and we're going to look at that here shortly. So many different kinds of applications using near-infrared spectroscopy: pharmaceuticals, food and beverage, agriculture, chemical, petrochem, medical, and the one we're going to be looking at closely today, polymers. So what you see on the graph here is the near-infrared spectra of four pretty common liquids: water, ethanol, benzene, and acetone. So near-infrared spectra are complex, and the overtone and the combination bands they're pretty broad, and they rarely lend themselves to any kind of visual interpretation. I want you to notice here how the two big water peaks around 1900 nanometers and around 1400 nanometers. Near-infrared is very good for measuring certain kinds of water measurements. I'm going to show you a few of those here coming up. So what we have here is an absorbance bond diagram. So these are different bonds, overtones, and combinations, and near-infrared spectroscopy requires the use of multivariate data analysis to extract the desired information that you want. So why is that? So if you look here, there's a lot of overlap between the different chemical bonds. So if you're measuring the absorbance at a single wavelength, you can't really tell exactly which bond is causing the change in the absorbance. So how do you get around that, or you get the information that you're looking for? So what you have to do is build chemometric models. So you develop those using reference values for the chemical and the physical parameters of interest, the near-infrared spectra that you collect, and then there's calibration techniques that you use. Two examples: principal component analysis that's used for classification, detecting an outlier if there's something strange about a sample. And then what's called partial least squares is the most common one, where you would use if you wanted to do a quantitative measurement. There's some different pre-processing methods that you can use before you do your modeling, apply it to your spectral data that could do things to help you out. For example, reducing the noise in your spectra. If your spectra are noisy, there's certain mathematical processes that you can use to reduce that. So here's a look at the three different measurement modes that you can use when using near-infrared spectroscopy. So the one on the left is transmission. So the light's coming out of the source, actually passing through the sample and getting collected by a detector. Examples of this is using cuvettes or vials, a flow cell in a process would be an example of transmission. Then you have in the middle what's called transflection. So transflection is similar, but what happens is the light passes through the sample, and then there's a mirror behind it, and then it reflects off of the mirror and back through the sample again. It's collected by the detector. So this doubles your path length, and this is a common technique for process probes that are used in liquid measurements. And then on the right, you have reflection. So the light comes out. This is non-contact. The light comes out of your source, is reflected off of your sample. There's a lot of scattering there, but some of it is collected by the detector, and that's where you get your near-infrared spectra from in reflection. So there's a lot of advantages in using spectroscopy in general over traditional methods. It's fast, it's non-invasive, it's cost-effective, requires little to no sample preparation. You don't have to sample from dangerous environments. You don't have to destroy your samples. It doesn't require any chemicals or solvents to be used, much less labor intensive. And then with my job as an applications engineer, my favorite advantage is that once you build your models, you have the ability to measure multiple parameters with a single light scan and spectra reading. And I'm going to show you here just in a few minutes how you do that. So near-infrared has some distinct advantages over other spectroscopic methods. So we're looking at a reflectance measurement here. So you see the light's going pretty deep into the sample there. So near-infrared light has pretty deep sample penetration. Diffuse reflected light can penetrate up to about 4 millimeters into powders. That's going to depend on your particle size, your wavelength, and your density. Requires little or no sample preparation. You could just put your sample in a glass vial or beaker because glass is transparent in the NIR spectral region. So having something in glass, it's not going to affect your spectra at all. The sample beam is large. It can go up to, some spot sizes can go up to about 25 millimeters. So it's very well suited for non-homogeneous samples. And then it's also very well suited for trace moisture measurements. So you saw those water peaks a few slides ago. Water is very absorbing of near-infrared light. So I did a study measuring trace amounts of water in jet fuel, and it was able to measure the trace water down to about 10 parts per million or so. So if you're talking small amounts of water, this is what you want to use. The flip side of that, if it's an aqueous solution and there's a lot of water in it, then the water is just going to absorb all the light, and you're probably going to have to use something else. But you're talking about trace water and gasoline, jet fuel, moisture in a pharmaceutical powder, for example, then the infrared is very well suited to do those kind of measurements. And then here we have a FT Fourier transform near-infrared spectrometer. So this uses a Michelson interferometer. So what this does is it uses an interferogram signal that is transformed into a spectrum of frequency versus intensity. So there's some advantages here. It's very fast. It measures all of your wavelengths simultaneously. You get higher resolution, higher signal energy. It uses an internal reference laser to accurately calibrate your wavelengths. You don't get any stray light with this. Stray light can be a real issue with dispersive type instruments. And then, back to me and my job as an applications engineer, these instruments are, they're pretty reproducible. So what that means is to transfer a calibration model that you build on one spectrometer to transfer that model to a different instrument, the requirements are pretty minimal for that. It's pretty easy to do, and with some other types of instruments that it cannot be so easy. So a lot of advantages to the FT instruments. And then here, and this is just to kind of, sort of begin to show you the advantages of using this stuff. This is a comparison of using NIR for some kind of measurement versus HPLC. So, you see there's a pretty substantial initial investment in that in the first year. But then after that, your consumables and your labor costs using the NIR method is greatly reduced. And again, you have the advantages that I've already discussed here, being fast, you can do it online, no sample prep, no chemicals involved. So the advantages of being able to use near-infrared over some traditional techniques are pretty vast, including the cost savings. So now let's take a look at some different polymer applications. So we looked at the absorbance bond diagram earlier, and near-infrared spectra, they result from the combination and overtone bands of CH, NH, and the OH hydroxyl vibrations, which are especially absorbing. So polymer chemistry and reaction mixtures, they contain organic compounds with these bonds that makes them very ideal for near-infrared analysis. You look at the list of the applications on the left here, it can measure both chemical and physical properties. So, you can use this stuff for all kinds of things, research purposes, quality control, specification testing, and also process control. So let's take a look at some of the chemical properties here. So I'm going to explain here in a second exactly what this model is and how you would go about constructing this. So this is hydroxyl number in polymer granules. So hydroxyl number is a very important final product quality indicator in polyols. So polyols are produced from reacting an alkaline oxide and initiator, usually ethylene glycol or glycerin, in a catalytic environment. And then you take these polyols and react them with isocyanates to produce polyurethane products. So to get the reference, the traditional method for getting this hydroxyl number value is you have to do a titration. You'll reflux it with an excess of acidic anhydride. Doing that, it typically takes 1 to 3 hours, and it uses large amounts of chemical reagents. So this is a partial least squares regression model. So how did someone, what did someone do to actually make this happen? So someone sat down with a near-infrared spectrometer, and they had samples of these polymer granules with the reference values already determined for the hydroxyl number. So they scanned the instrument, or they scanned the samples with the instrument. So you've got near-infrared spectra matched up with what the hydroxyl number is. And then, you used software to build your chemometric model. So what we're looking at here, we're looking at one of these models that someone actually constructed. So this plot, what it's comparing is the value that was predicted from the model versus the value for hydroxyl number that was determined through the titration. So once you have one of these models, then you literally feed your near-infrared spectra into it, and it will give you a value for the parameter that you want to measure. So this is, a predicted versus measured plot. You see some statistics here, and I don't want to harp on all this too much, but I just want to, because we're going to look at a few more of these, and I want you to understand what you're looking at. So this R squared is a correlation coefficient. 100 will be perfect. You're never going to get that. But basically explaining how well the quote unquote data fits. The RMSECV is an error measurement that you get from cross validation. So what I mean by cross validation is you make one of these models, and then you can do it where it'll pull a couple of the samples out, reconstruct a new one, and then predict the values for the samples that you pulled out of the model from that. So it's a way to validate your model. So basically a type of error measurement. This RPD is the ratio of the standard error of prediction to the standard deviation. basically a measure of your model quality. And then here at the bottom left, we have what's called rank. So rank could be also defined as factors, principal components, and that's basically a measure of the number of iterations that the model needs to perform to be able to fit the data. So let me explain exactly what I mean by that. So for example, if you're doing moisture in a pharmaceutical powder, you're in a controlled environment, nothing's really changing. You saw, and I've explained how water is very absorbing of the near-infrared light. So, it's going to fit the data nicely and pretty quickly to those big water peaks. And for something like that, you're going to see, the rank's going to be 1 or 2. Now, if you're talking about a natural product, say, something agricultural that's, grown outside in the field, and you're using different kinds of soil, different kinds of fertilizer. If the field's really big, maybe some areas, it's getting more sunlight than others, more rainfall, whatever it may be. So those kind of things can introduce changes into your near-infrared spectra that are not related to the parameters that you're actually trying to measure. But the way you get around that is if you put enough samples in your model that incorporate all this variability, this math is powerful enough that it will, the model will learn to, quote unquote, overlook the differences in the spectra that are caused from the natural variability and just focus on the changes for what you're trying to measure. So, that brings in a challenge with natural products. It can be a little tougher as well. They have pre-built calibrations for these models. So, if it's something, that's already been, you have a pre-built calibration, it may just work for your samples. Your samples may be a little different, like for polymers, for example. Maybe you use a different additive than one that was in the reactor when the pre-built calibration was built. But you take some of, your samples and the spectra from those, add them to the pre-built model, and just as I explained with the agricultural product, the model learned to overlook the differences in additive and just focus on what you're trying to measure. So that's called making a model robust per se. So to do this, you can get different levels of support. Some companies have people who are experts in this stuff, and you send them the instrument and they just go to it. Some places, you train them how to do it. You would get someone like me in there to show them how to do this. And then there's other places where, they literally just want to push a button and get the result they want. And as far as, doing this modeling work and validating and all that, they want support to do that. And that can be done as well. Just, send us the bill. And some of the software advances that are happening now have really facilitated the ability for, outside help to be able to do your modeling or whatever kind of support that you want. So let's look at a few more of these chemical properties. So this here is acid number. So acid number is defined as the mass of potassium hydroxide in milligrams that is required to neutralize 1 gram of a chemical substance. A titration is required, and it's a measure of the number of carboxylic acid groups in a chemical compound or group of compounds. You take a known amount of sample, dissolve an organic solvent, and titrate it with the potassium hydroxide using a color indicator. So this is also a very important number in the polyol manufacturing, and the sum of the acid and the hydroxyl numbers is known as the N group number, which is an important parameter as well. So here's another one of those calibration models like we looked at a few slides ago. So this is for isocyanate concentration in polyurethane synthesis. So you form polyurethanes by adding polyols and with the NCO, the isocyanates, with the catalysts and additives in the reactor. So the first step is to produce a precursor to the final product by the reaction of a polyol with excess isocyanate. So the ratio of the reactive groups is very important, as you want to leave some reactive NCO afterwards. You have to leave some left because you make your initial polyurethane, and then after that, polyurethane is formed into all different kinds of products: foam, lockers, insulation, adhesives, fibers. So you need to have some left over, and you need to have that pretty specified. So it's very important to determine the proper endpoint of reaction. Isocyanate's a very hazardous material, and pulling the samples out is very difficult for analysis. So you see the numbers here, the R squared and all that. This is a very solid model as well, especially considering that it only has 15 samples. So here's one that's a little bit different. So this is silicone oil. So silicone oil is any liquid polymerized siloxane with organic side chains. The polymer backbone consists of alternating silicon and oxygen atoms. There's a very high commercial interest in this stuff because it has high thermal stability and lubricating properties. And yeah, this is used in numerous industries as lubricants, thermic fluid oils, hydraulic fluids, including electrical, plastics, rubber, paper, textile, paint, automotive, constructive, you name it. And sometimes to get exactly what they want, you have to do blends of different oils. So what you're looking at here is 4 separate calibration models for the silicone oil. So what they did was they actually got known samples with different percentages of this A, B, and C, and D, and built calibration models from the near-infrared spectrum to determine the blend percentage. And you can see from the numbers here that this one worked pretty beautifully as well. So those are some chemical properties that you can use for near-infrared spectroscopy and polymers. Let's take a look at some of the physical properties now. So this is a near-infrared spectrograph of 3 different density levels of polyethylene. So density is defined as the ratio of the molar mass and molar volume at a given temperature and pressure. And it's very important. It can be used to calculate the percentage of a polymer that is crystalline. So polyethylene is a thermoplastic that's made through the polymerization of ethane. It's used in a lot of things, packaging films, toys, pipes, and housewares. And there's been different levels of density that have been developed based on the density of the material and the branching of the molecular chain. So the 3 types that you're looking at here are high density polyethylene, low linear, and low density polyethylene. So you could use NIR in some different ways in this. You could make a pure classification model where you were just trying to identify which of the 3 density types it was. You could use the actual density values to make a quantitative model to determine the density. And sometimes those work within each other. You have the qualitative model where you pick what kind it is first, and then within those, then you would have separate calibration models for the quantitative number of density within the different 3 values. And another very important physical property of polymers is viscosity. So viscosity is a measure of the resistance of a fluid to deformation at a given rate. Viscosity measurements are a way to determine the size of the polymer, which leads to the chain length and the molecular weight. The viscosity of a polymer is always larger than that of the corresponding monomer, and it increases rapidly with increasing molecular weight. So this is a very, very important parameter of the progression of reaction in polymer formation. So this was a fairly new study, and I wanted to include it. So this is actually measuring a model measuring the viscosity of shampoo, the PA per second you hear. That's just a different way to express the standard viscosity unit of Newton second per square meter. And again, you see the statistical numbers here are pretty good, so this model worked well. And then another very important physical property in polymers is melt flow index. So melt flow index is a measure of the ease of flow of a thermoplastic polymer and is a measure of the resistance of the polymer melt at a given temperature under a given force for a predetermined amount of time. It's an indirect measurement of molecular weight with a high melt flow rate corresponding to the lower molecular weight. So melt flow index is inversely proportional to viscosity, although viscosity is dependent on the applied force. You could calculate a melt flow index ratio at 2 separate pressures, and that's a measure of the broadness of your molecular weight distribution. So very, very important. When engineers are designing polymers, you need to keep the melt flow index high enough to form the molten polymer into the desired product that you want, but you need to keep it low enough that the mechanical strength of the finished product is going to be sufficient to meet the specifications that you're looking for in the final product. And one more physical property here of polymers. So now we're getting a little more on the atomic level. So this is tacticity. So tacticity is the steric order of atoms in a linear asymmetric polymer chain. So if you look on the graph on the left here, there's 3 different types. There's isotactic, where all the R groups are on the same side of the chain, syndiotactic, where the R groups are on alternate sides, and then atactic, where the R groups have a random distribution. So polymer tacticity has a very strong effect on how a polymer melts, how soluble it is, and its mechanical properties, especially the glass transition temperature. So the greater order in isotactic and syntactic chains favors crystallization. So the reference method that is required to do this measurement is NMR, which it's very expensive, it's time consuming, and it requires skilled labor as well. And as you see here on the right, another calibration model for determining atasticity in polypropylene granules, and this one came out pretty well as well. So we've looked at some applications here, different things you can measure. So let's take a look at some of this stuff in practice and how it's actually used. So material ID and sorting, determining moisture content, those are big ones. So they use these spectrometers to sort out recyclable materials to identify different kinds of polymers when they're sorting recyclables. And that's kind of progressing. They're using it to identify biodegradable plastics to be able to pull those out, and they're even using it for identifying marine waste. So this junk that comes up on beaches in the ocean, they're pulling out. They're actually doing some studies to be able to identify the stuff that they find using near-infrared spectroscopy. And then of course the monitoring and the reaction, and of course you can use it for a final quality check to make sure your product is what you want. So here we have two examples of the recycle sorting that I just mentioned. So the graph on the left is near-infrared spectra of nylon 6,6, polyethylene, and polypropylene. You see they're pretty distinct and they're pretty identifiable here. And then the one on the right is also 5 different types of polymer. So the one that's really of interest is the royal blue one. So the royal blue one, the PLA, is polylactic acid, which is a biodegradable plastic. So you can see if you wanted to be able to identify that stuff out of other types of polymers, that you would be able to do that from the near-infrared spectra. So if you look at these graphs here, so I had mentioned some of the data pre-processing that you can use on your spectra to help you with your modeling and stuff. And both of these kind of show that. So I just wanted to touch on it real quick. So this SNV that you see that here, and then here you see the first derivative. So those are 2 different types of processes that you can use. So the SNV is a normalization function. You subtract each spectrum by its own mean and divide it by its own standard deviation. So each spectrum will have a mean of 0 and a standard deviation of 1. And what that does is it reduces the effects of light scattering. If you have different particle sizes and you want to reduce that effect, it can do that. And then it can help with baseline shift. So what I mean by a baseline shift, if say you had a probe and something moving under it, and the stuff wasn't even and there was a distance, the distance varied between the samples and the light source, that would create kind of a vertical shift in your spectrum. And doing this process can help eliminate the effects of that. And then the first derivative is the rate of change of absorbance with respect to the wavelength, and that helps if you have noisy spectra, that can help reduce the effects of that. So similarly, if you had spectra of different kinds of marine waste, you could do the same thing. This ID stuff can be big. I did a study with catalyst identification in the past. So this place made the big long acrylic sheets that go into hot tubs and those kind of things, and they used 5 different kinds of catalysts, and they were having a problem with putting the wrong catalyst into the reactor by mistake. And when they did that, it made a big mess. They lost the product. Downtime, they had to go in and high pressure wash the inside of the reactor. So they sent me samples of the 5 catalysts. I scanned them, did some of this data pre-processing, and there was enough distinction in the near-infrared spectra to be able to use that to identify what the catalyst was. And it was a beautiful setup. They actually had a flow cell, and it would scan and identify, and if it matched what it was supposed to be, the valve would open and let the stuff in. And if it wasn't, then they could stop it before any kind of damage is done. So let's take a look at now sort of more the manufacturing and how near-infrared spectroscopy is used in that. So what you're looking at here, it's an incoming inspection of tank wagons. So the rail cars that you see on the left here, they are bringing in monomer products for making polymers. So what happens here is the product gets pumped out and it is scanned with a flow cell. And if the scan is correct and the stuff is what it's supposed to be, then it'll open it and let it in. and if it's not, then they'll turn it off and keep it from going into the tank and then eventually into the reactor. So where this guy is holding his hand here, as you see with my pointer, is this spot right here. So what's happening is the light is coming out of here, the sample's in this flow cell, it's passing through it and then going back through to the detector and identifying what the product is supposed to be and making sure that it's the correct thing and you don't send the wrong stuff into the tank. And here we have a actual reactor where they are monitoring the isocyanate concentration in polyurethane manufacturing. So right here, what we have is from that application. On the right, we have the near-infrared spectra, and it's pretty easy to take a look at the spectra and see that clearly something is changing as the reaction is progressing. And then on the left is another one of the calibration models. Looks like this was done in Germany or someplace where they speak German from the words there, but you see the numbers and you see the plot fit, and you see that you know, this one worked pretty beautifully as well. And to prove that to you, what we have here, so this is a plot of a comparison of the values of samples from the titration and laboratory analysis versus the near-infrared prediction from the spectra that was collected during the reaction and the calibration model that was used. So you see they match up pretty well. If anything, there's more variability in the titration analysis. It's kind of hard to say why that is, but it could potentially be that there's more air in the titration. You pull these samples out, and certainly they could potentially change. And said you have not only you may have less air possibly, but there's a lot of advantages as well. No sampling, it's faster, done in the reaction, and you don't have to worry about your sample changing. And here's another setup where with polyethylene film manufacturing. So on the left here, you see some values determined from the near-infrared models for density and melt flow index. And then now we're getting our first look at a multiplexer spectrometer. So this instrument, you see it's got 4 sets of fibers and probes coming out of it, and they're monitoring this entire process, the polymerization reaction before it goes into extrusion, as it's coming out of extrusion, and then before the filming starts. They're using one instrument to monitor 4 different parts of this process, and that's a big deal, and we're going to look at that a little bit more closely coming up here in a minute. So I wanted to show you this. This is with the petrochem. It's a petrochem application, but I thought it was a really good example of just how you can use these instruments for process control. So ethylene and propylene are produced from virgin naphtha in steam cracking plants through pyrolysis, which consumes a very large amount of energy. So if you look here at this Spiro, so Spiro is a software simulation program. It's for the simulation and optimization of the steam cracking progress, as well as other processes in the ethylene furnace. So it gives you an accurate prediction of the ethylene yields for feedstocks at any given set of operating conditions. So optimizing your process is of fundamental importance in terms of achieving your profit margins. Advanced process control allows for the maximum yield of ethylene and propylene at any given energy usage level. So there's a lot of components here, and you'd have to use GC to determine this, and that's just impractical for real-time monitoring of multiple components. So what they're doing is they're predicting the composition from the near-infrared spectra, using that as input data for the Spiro software. And then the most important output parameter is this COT, which is the cracking output temperature. So they determine that, and then from there, the advanced process control system can optimize the different plant operating variables. And as you see here, the near-infrared and the chromatography are both in very good agreement. This is for the propylene yield and the ethylene yield. And here we have, so this is more for pharmaceuticals, but it's providing a pretty good framework for how some of this stuff is being done these days. So I wanted to show it to you. So this is process analytical technology. So PAT is an FDA pharmaceutical initiative, but some of the principles are starting to take hold in other industries. So the idea behind this is that you design, analyze, and control manufacturing through the measurement of process parameters which affect quality attributes. A big part of this is the batch versus continuous testing. It requires multivariate data acquisition and analysis. And in order to do this, it does require process analytical chemistry tools, of which near-infrared spectroscopy is a big part of that. So with this, you have continuous improvement tools, and absolutely 100% doing this stuff is going to result in improved workflow. So there's some crossover between the polymers and pharma and the medical. You see the medical plastics and biodegradable materials. Certainly going to help reduce your resources and improve the environmental impact. And there's been some challenges in software and hardware that have hindered the advance of doing this stuff in other industries, but they're making some advances in doing that. And I'm going to show you what a few of those are coming up here in just a minute. So let's look at some of the different instruments that are used to do this stuff. So this is the Brooker Tango. So this is your laboratory go-to instrument. This is a great one for checking your incoming products, doing a final quality check. The best way I can describe this thing is as a routine analyzer. It's very easy to use. It's icon-based driven. You have a touch screen that's no different from a tablet or iPad. With this thing, you literally push a button and you go, and it does what you have it set up to do. And here we have the Brooker MPA. So that's the multi-purpose analyzer. So this is kind of like the jack of all trades. You can do all different kinds of things with this one. You see with the sample compartment, you have a vial in it. The integrating sphere you could use for reflectance measurements. External transmission you could use for liquid measurements and maybe some kind of powders. And then the fiber optic probes that can be fit for transmission or reflection. So this is the patented Brooker rock solid interferometer. So if you look here at these mirrors, they are cubed cornered. So a traditional Michelson interferometer has flat plane mirrors, and this one has cubed corners on it. So that gives you some real advantages. It makes it non-sensitive to vibrations, non-sensitive to temperature fluctuations, very high repeatability, excellent accuracy, high resolution, and the thing is permanently aligned. And then applying to me with the calibration transfer. So you build a calibration on one of these MPA instruments. You can transfer it to another MPA instrument. You could transfer it to an older model of an MPA instrument. You could transfer it to a Tango instrument. You could transfer it to a matrix process instrument, which we're going to look at next. You probably could even transfer it to another type of spectrometer altogether, and that's huge. In the past, I worked with AOTF instruments, which used a vibrating crystal to diffract the light. So, they had some cool advantages, but one problem with them was you can't reproduce a crystal. So you couldn't reproduce the instrument. So you build a calibration on one instrument. It may not work on another instrument. There were some things you could do to try to make it work. Sometimes it worked, sometimes it didn't, but you had to put a lot of labor intensive stuff into that. With these things, you can basically with any type of FT instrument, you can literally transfer it to any other type of spectrometer, any type of calibration that you use. The important thing to note with that is that you can build your calibrations in your laboratory. You can sit in your, cool, air-conditioned, temperature-controlled laboratory, build your calibration with your samples, and then when you're ready to start doing your process monitoring, you can take those calibrations and transfer them to the process instrument. And then here we have the Brooker Matrix F. So this is the process instrument. It's a 6-channel multiplexer. It can be fit with something to give you some additional channels if you need to do that. So you can measure 6 and potentially even more points in a process with a single instrument. And so you're looking at here some different kinds of probes. So on the top left, we have the transflectance probe. So that's used for process liquid measurements. You see the little gap there, the liquid would go in that, light passes through it, reflects off the mirror, back through the sample and back to the detector. On the top right, we have the handheld reflectance probe. That is really good for raw material ID, and there's also a transmission version of that as well. And then across the bottom, there's 2 Q412 non-contact probes. So so that's used for reflectance. It doesn't have to touch the sample. The one on the bottom right has the transflectance probe in it as well. So if you have 2 different kinds of probes with the same instrument, we could fit the instrument with special optics to be able to use both types of probes. Basically, you have a probe for any kind of sample type that you want to use, gas, liquid, slurry, solids, anything you want, there's a type of probe to be able to measure it. So here's a place where they're actually using these instruments, and this has been going on for quite a while. So they're using the Bruker Matrix F for polyurethane manufacturing. So this was implemented all the way back in the early 2000s, and it is still going on today. So if you don't believe me, take a look at those monitors there. When I looked at those monitors, the first thing that went off in my head was the AOL sign-in and You've Got Mail. They've been around and been there for quite a while. So this place actually uses 7 Matrix F instruments, and then each of them is fit with 2 extra multiplex channels. So each one of those 7 instruments can measure up to 8 points in the process, and they have 1 spare instrument. So in total, there's 56 measurement sites, and they are using approximately 450 different near-infrared methods and models to monitor the stuff there. So they don't have to do any laboratory analysis. I imagine they do some, to kind of check the models and validation from time to time, but they're not required to do any laboratory analysis. And I imagine they keep pretty busy there. If I worked in this place, I would probably never, ever get a day off. So I'm going to show you here 2 application notes where the Bruker Matrix F is actually being used. So this one's for polymer resin manufacturing. So here it's very critical to monitor the acid number and the hydroxyl number. So from that, the reaction endpoint can be accurately determined. They can avoid bad batches, and the quality of the end products can be kept within NIR specifications. And getting the first look here of right here, some of the process communication protocols that are used to transfer the information that you get from the spectrometer to their distributed control system. So this application note is available. If you want to look at it in more detail, contact us and we'll be glad to pass it along to you. And then here from that, 2 more of these near-infrared predicted versus the reference value plots for the acid number and hydroxyl number. But beautiful, these look really, really good. And then similarly, here we have the trimaletic anhydride using the Bruker Matrix F. So pretty similar, a little bit different. So in this one, they are doing a batch reaction with pseudoconine with acetic acid in the presence of water and an oxidation catalyst. So it's a batch reaction. They have 2 tanks, the acetic acid mixtures in one, the pseudoconine in the other, and then they monitor the feed of the batch. So doing that, they can tightly control the conversion rate of the reaction and then improve the yield of the next step of the reaction, which is distillation. We also have this application note available as well if you want to take a closer look. And then here are the 3 calibration models for acetic acid, pseudoconine, and water, and those look really good as well. So we've come a long way from the AOL dial-up days, and I know we all know this, we're all living it every day, but I wanted to just touch on it briefly here. So Industry 4.0, the current industrial revolution that's going on right now. So Industry 4.0 is the ongoing automation of traditional manufacturing and industry using modern smart technology. So we're seeing this everywhere, and it's being used with the spectroscopy too. I'm going to show you here how it's being used in some software advances that's really helping to facilitate this. So here we have the Bruker CMET software. So this is the link between a process analyzer and the customer's distributed control system. So this is split into 4 modular sections. You have your spectrometer setup where you define your general measurement points and measurement parameters, your product setup where you configure product specific parameters such as your calibration models, your storing options, your product information, your input output setup. So that's where you're going to set up the communication protocols with the DCS, and you can use different ones with this, the 420 analog milliamp, profit bus, DP, Modbus. There's a bunch of different ones you can use here. And then from all that, you get what's called your scenario setup. So you assign a product to a specific measurement point and define start triggers and output signals. And then the entire setup is then exported as a scenario map. One scenario map, which includes all the necessary information that you need to be able to run a scenario in the real runtime mode and actually use this to be able to control your manufacturing process. And then on a bit of a bigger scale here, so this is the Bruker ONET software. So ONET is a server-based application accessing a browser-based web interface, basically a web UI that allows you to set up, administrate, and control a network of FT-NIR instruments from anywhere in the world. So the data is measured on local spectrometers, it's centrally stored, but all the data and required files are still available locally. So, if you're halfway across the world and your Wi-Fi goes down, they're still going to be able to analyze the samples and store them locally until the thing gets backed up. So this is big for providing the application support that I talked about. So, if it's a place where, they just want to scan the samples and let, someone else do the legwork, you can have something like this set up where, someone far away can go in and do your application support for you. And there's just some different kinds of probes and flow cells that are used for process measurements. There's always new designs, new upgrades. That's always going on with, this stuff with, fibers, probes, flanges, interfaces. They're always making upgrades to help facilitate better performance in high pressure and high temperature manufacturing environments. Certainly we could offer you some more details on that if you reach out to us. And so, I'm not a fan of, signing up for something with, misleading headlines, fake news, whatever you want to call it. And I did. The title of this does begin with leveraging the power. So I'm going to wrap this up here by doing a little bit of a recap and showing you just what the power is of using FT-NIR spectroscopy for polymer manufacturing. So the power. The infrared spectroscopy offers a fast, non-invasive method for monitoring both chemical and physical parameters of polymers. No sample prep is required, no collecting samples for online monitoring, no sample destruction. It's cheaper and safer than wet chemistry and chromatography methods. And again, my favorite, you have the ability to measure multiple parameters from a single light reading and spectrum. So it's expanding from an offline laboratory and benchtop method to a real-time process control tool. And advances in software pushed towards Industry 4.0 have facilitated the use of NIR for process monitoring. Improved fiber optics, interfaces, flanges, and probes in high pressure and high temperature environments, increases the accuracy of your readings and helps prevent hardware breakdowns. And the easy calibration transfer makes building models simple in the laboratory, and then you can transfer them to your process instruments, which makes FT-NIR spectroscopy the ideal tool for process monitoring. So ultimate result of all this is improved product quality, optimization of resources, reduced downtime, less manpower, improved worker safety, and maximizing your profit margin. So early on in this, I showed you 4 different chemical properties and 4 different physical properties that you can measure using near-infrared spectroscopy. So I've listed them here, and you have also a list of the reference methods that are used to determine them. So these first 3 require titration. It takes an hour, maybe multiple hours, requires dangerous chemicals. The silicone oil blends will require HPLC, which is very expensive and very time consuming. And then the 4 physical properties. So the first 3, those instruments aren't really all that expensive, but you do have to use them offline. It does require, sampling from the dangerous environment. But then the atasticity requiring the NMR, it's very expensive, time consuming, requires skilled technicians and labor. So, you could go through all this stuff and all this mess, or you could get all these measurements all at one time in one 30-second scan and light reading using FT-NIR spectroscopy. Then, if you want to get your superpower, you can use a 6-channel multiplexer and multiply all your savings by 6 and measure 6 points in one process using one spectrometer. And I don't think I need to show, a return of investment or a whole bunch of money numbers here to show you just what the pure financial benefits are of that, much less all the other stuff that I went over here. So I thank you for tuning in, and I think now we're gonna turn it over to Brian and take some questions from you.
Yeah.
And I welcome any of you that don't have me on LinkedIn. I welcome any of you to reach out to me and connect with me. I'd love to discuss this stuff further if you care to.
Right on. Thanks, Rob. That's fantastic. And I just want to remind everybody here that would like to ask some questions down in your side panel there. Feel free to type in your questions real quick. We got a few in here, and we got a little bit of time left. And if for some reason we just run out of time and we can't get to all your questions, we will make sure we follow up with you and respond to you directly. So Rob, we got a few here to get us going. So first question is there a good way to know when you have enough samples for a good starter calibration?
That's a very good question. So, what you want to do is you want to take a look at, well, one big thing is, what's called a design of experiment, where you kind of sit down on paper and sort of incorporate, I mentioned that, you can have some sort of different variables from the natural products, for example. So that's one thing you could do to sort of take a look at, maybe how different variables could affect, your final result. But, just sitting down, getting your samples, and then taking a look at, creating a first model, and then, you take a look at those statistics. You look at your R-squared, you look at your error prediction. You take that model, and then you get some new samples, and you scan the spectrum, and you do prediction. This software, you can do, offline predictions pretty easy, where I mentioned the cross validation, where you actually, pull some samples out as you're making the thing. You can do that once you have your model. And the process that usually happens is, once you have one of these set up and you're, scanning and getting your predicted values from time to time, you pull out samples and you go do the reference method. And then you take a look and you say, okay, well, what did the near-infrared predict? And what is the actual reference method? And you can compare that to validate your model, but then you can also take that sample and add it into your model. So you can sort of validate these models, but continue to build on them at the same time. It's important to, look and see, is anything changing in your process? The temperature can have effects on the infrared spectra. So, if you're in a place where, it gets really hot in the summer and it gets really cold in the winter, and that's sort of affecting your samples, that's something you got to take a look at. So, there's no sort of, magic formula that, hey, you need like this many samples for, this particular measurement. That if it's something simple in a controlled environment, and you got sort of a tight, thing between the specs, and it doesn't really go out of that too much, then, you probably don't need that many. When you're dealing with the natural products and incorporating more sources of variability, then you kind of want to like continue to build on it as time goes by, especially with the natural products, like adding like, harvests in subsequent years and that kind of stuff. So there's no magic formula. You just kind of know sort of what you're doing. But the initial model building and taking a look at the statistics you have, that's definitely the first step, and then taking it from there.
Nice. And a quick follow-up question that just came in that I think would be a good one to add in here is how do you know when a sample truly is an outlier, or if it's one you should include into your model?
That's an interesting question, and a very good question. So, the math in said, and I don't want to get, too deeply into the actual like mathematical techniques, but these software programs where you do the chemometrics, there's different, sort of plots and things that you can look at that sort of show whether something is an outlier or not. But you have to analyze those carefully, because you need to make sure whether it's really an outlier or not. What you can do is, you see these samples that really don't fit into the model per se. You might have noticed, and I didn't really touch on this, but some of the model graphs that showed you had a couple of like red dots on them, and that probably did mean that they were, an outlier, didn't, fit in the way the rest of those do in some reason. So, you can pull all the samples that it says are outliers out of your model and then recalculate it. And then, your statistics are going to get better. Your R-squared might go up and your prediction error might go down. But then using the model in practice, you may have removed a source of variability from the model, like something in the spectra that was changing for whatever reason, by pulling those outliers out. And then if you scan a sample to get a prediction that, has whatever that source of variability is, then it's not going to be able to predict it well. So the principal component analysis that I mentioned, that is sort of a straight classification. So you get in those what's called a scores plot, where, like say for the 3 different density levels that we saw, if I was scanning those, I should, and I did this, PCA analysis, I should be able to look at this scores plot and sort of show, 3 distinct groups on that with the catalyst ID. It should, if I collect 10 spectra of each, they should be all kind of grouped together. So, when you do one of those, and that usually is the very first thing that you do after you collect your spectra, is just sort of do this, sort of PCA classification analysis. So if you look at one of those and you see, 3 groups, and then one of them's way out in left field, then something's wrong, and you want to take a closer look at that. Maybe you didn't have your sample placed right. Sometimes you can just tell by looking at the spectra if it looks all goofy, the signal's way lower, or way higher. Some of it's saturated the detector or whatever. So there is a sort of a science and a technique to it. But what you definitely don't want to do is see models or see outliers that the math shows it's an outlier and just pull them all out, because even though it may make the statistics look better in practice, it may not work as well.
Nice. All right, so another question that came in, is it possible to use online NIR to monitor and control the curing process for UV activated resins?
I would think so. I mean, the resin manufacturing, we saw one of those earlier, and you're sort of measuring the same things. From the best of my understanding, using the UV just in practice kind of just speeds it up. It makes it go faster, and if that's the case, then I would think that getting your your readings quickly and being fed in real time, as opposed to pulling the samples out, doing the traditional methods, would be more beneficial than ever. So that is an interesting question. It's something maybe I'll dig in and do a little more research into that. But I would say that the resin manufacturing is definitely a documented, proven method. We saw it here during the show, and I don't think the doing it the UV way would affect that too much. If anything, it would probably be even more beneficial to get your readings quickly.
Yeah, and I think probably even with that non-contact emission probe would probably be a good way to monitor these curing processes, especially if it's like a resin that's been sprayed on something, or a coating of some sort or something like that. So, all right.
Yes.
So, another question, I think this might be the last question we have time for. Can NIR be used to measure particle size in the suspension polymerization process?
Yes, particle size could definitely be measured by near-infrared spectroscopy. So get away from the polymers for a second, because there's another project that I worked on fairly recently. So hardness in wheat is which is correlated directly to the particle size. You can not only use NIR for that, but it's actually a certified AARC method to be able to do that. So changes in particle size will absolutely 100% afford a change in your near-infrared spectra. So yeah, that's been measured in many different kinds of things. Depending on what you're trying to model, I had mentioned, like the different particle sizes, it may have an adverse effect, because it's one of those sources of variability. So if that's not what you're trying to measure, then you want to maybe reduce the effects of that. And you could do that with one of the data pre-processing methods like the SNV that I showed you earlier. But if that's what you're actually trying to model, or be able to measure using the calibrations and the near-infrared spectra, yes, particle size is something that absolutely will affect your NIR spectra and can be modeled, and you could monitor that for sure.
Nice.
The biggest
Well,
issue there would be with as you mentioned, with the emission probe, you'd have to make sure you had a good solid sampling method. But that's been done before, and I'm very confident that yes, you could definitely measure particle size using near-infrared spectroscopy.
fantastic. Well, for I think that's about all the time we have for Q&A. For those of you that we didn't get to your questions, fear not, we will respond to you directly with email and follow up with you directly. But before I close up, I just wanted to let everybody know about an upcoming webinar we are hosting next month. On June 9th, we'll discuss the analytical challenges faced by chemical manufacturers and how a robust online mid-IR process monitoring solution is revolutionizing the industry. So check out lqa.com/webinars to register for this webinar. I wanted to send a big thank you to Robert for presenting today for this webinar. As a registered guest, you will receive an email within the next few days or so with a link to this recorded webinar. We encourage you all to visit our resources page on lqa.com for future webinars and some of their details, and access our library of our recorded on-demand sessions. So again, a Big thanks to you all for joining us, and I hope you all have a great rest of your day.
Thank you, everyone. Have a great day.